Hello everyone and welcome back to the Jamaican Geologist YouTube channel. This is episode 15 in the Geology Foundation Series, and today we're diving into the topic of natural hazards. So what exactly are natural hazards? Simply put, they are naturally occurring phenomena like earthquakes, hurricanes, floods, or volcanic eruptions that pose a risk to human life, property, and livelihoods. Now, here's where there's an important distinction. A natural hazard is the potential threat. It only becomes a natural disaster when that hazard collides with a vulnerable human population, leading to loss of life or property damage or some other major disruption. That's the widely accepted definition, but here's where it gets interesting. Some scholars argue that there really isn't such a thing as a natural disaster, and their reasoning is hazards may be natural, but disasters are shaped by human decisions. Where we build our homes, how strong our infrastructure is, and how prepared communities are for emergencies. For this channel, though, we'll be sticking with the widely accepted definition. Hazards are natural phenomena, and natural disasters occur when those hazards impact natural human populations. Now, natural hazards can be grouped into two main types. There are hydrometeorological hazards, and then there are geophysical hazards. Hydrometeorological hazards include hurricanes, floods, tornadoes, and blizzards. Basically, hazards driven by water, wind, or snow. Geophysical hazards, on the other hand, they include earthquakes, volcanoes, landslides, and tsunamis, all of which originate from processes within the Earth itself. For this episode, we'll be focusing on geophysical hazards. We'll explore the science and mechanics behind them, how they form, why they occur, and the forces driving them. So with all that being said, let's get started. So, simply put, an earthquake is when the ground suddenly shakes because of movements deep inside the earth. And sometimes that shaking can cause serious damage. They occur when stress builds up in the crust, usually along faults, and after a period, that stress is suddenly released. This is essentially the elastic rebound theory, which explains that rocks bend under stress until they snap back, producing seismic waves. So at a fundamental level, that's how earthquakes occur. I spoke about the different types of faults where these types of movements occur in a previous episode, so I won't get into that here, but let's talk about the types of seismic waves. Earthquakes generate two main types of seismic waves: body waves and surface waves. Body waves include P waves and S waves, which travel through the Earth's interior. P waves are the fastest, moving in a push and pull motion like the compression and release of an accordion or those slinkies we used to play with as children. S waves are slower, shaking the ground side to side like the motion of a rope being flicked. Surface waves, on the other hand, travel along the Earth's surface and are usually the most destructive. Love waves move the ground horizontally, while Rayleigh waves, they create a rolling motion, and together they cause much of the damage we see during earthquakes. The underlying geology also plays a big role in how earthquake waves behave. For example, solid rocks like limestone and volcanic rock tend to transmit seismic wave a little more efficiently. So the shaking is sharp, yes, but it's short-lived. In contrast, softer materials such as alluvium or loose sediments can amplify the shaking, making it last longer and often cause more damage. This is why areas built on filled land or river valleys often experience stronger ground motion compared to nearby regions on solid bedrock. Another effect linked to soft ground is liquefaction. This happens when water-saturated soils like loose sand or alluvium temporarily lose their strength during intense shaking. In simple terms, the ground starts behaving like liquid instead of a solid. Buildings and roads can tilt, sink, or even collapse because the soil beneath them can no longer support their weight. Liquefaction is one of the major reasons why earthquakes in coastal areas, river valleys, or reclaimed land can cause such devastating damage. This is what happened to the Giddy House at Port Royal during the 1692 earthquake in Jamaica. So volcanoes form when molten rock or magma rises from deep within the earth and makes its way to the surface through the cracks in the crust. Over time, as the magma cools and hardens, it can build a mountain-like structure, what we recognize as a volcano. This process happens mostly at tectonic plate boundaries. At divergent boundaries, plates pull apart and magma rises to fill the gap. At divergent boundaries, plates collide and one plate is forced down into the mantle, creating magma that can erupt. Volcanoes can also form at hotspots, which are columns of superhot magma that rise from deep within the mantle and melt through the crust, even far beneath the plate boundaries. Repeated eruptions, along with the accumulation of lava, ash, and other volcanic material, gradually build up the volcano over time. Not all lava is the same. Mafic lava is hot and fluid, traveling long distances, while felsic lava is cooler, thicker, and often more explosive. Eruptions can produce lava flows, pyroclastic flows, fast-moving clouds of hot gas and rock, and lahars, which are deadly volcanic mud flows. So landslides happen when rock, soil, and debris move down a slope, and they can occur on steep mountains or gentle cliffs. They are a type of mass wasting, which is just a fancy way of saying gravity pulling material down a hill. There are several types of landslides, including falls, topples, slides, spreads, and flows. Common examples are rock falls and debris flows, and the debris flows are also called mudslides. Landslides usually happen when gravity overcomes the strength of the slope materials. Triggers include heavy rainfall, snow melt, rising groundwater, earthquakes, volcanic activity, and even human activity like construction or deforestation. Most landslides are caused by a combination of factors. For instance, a slope weakened by weathering might collapse after a storm or an earthquake. So tsunamis are giant waves caused by sudden movements under the sea, such as underwater earthquakes, volcanic eruptions, or landslides. The most common cause is an earthquake at a subduction zone, where one tectonic plate dives beneath another. When the seafloor is suddenly displaced, it pushes huge volumes of water, generating waves that can travel across entire oceans at incredible speeds. As these waves approach shallow coastal areas, they grow in height, often leading to devastating impacts on coastal communities. Tsunamis are a dramatic reminder that plate tectonics don't just shape the land, it also affects the oceans, sometimes with catastrophic consequences. So it's one of those things that really goes without saying. You've probably already seen why this is important. I mean, studying earthquakes, volcanoes, landslides, and tsunamis isn't just about understanding dramatic natural events. It helps us to predict risk, prepare communities, and even save lives. By knowing how these hazards work, we can plan safer cities, respond faster to disasters, and better understand the powerful forces shaping our planet. So, that's a look at geophysical hazards: earthquakes, volcanoes, tsunamis, and landslides. And we explored the science behind why they happened. Notice how many of these hazards are linked to plate tectonics, which we explored back in episode 12. Earth is a dynamic, ever changing planet, and understanding these processes helps us prepare for and respond to the forces of nature. And in the next episode of the Geology Foundation series, we'll dive into paleontology and the fascinating world of fossils. As always, thanks for watching, and I'll see you next time. Take care.